If we have a temperature increase of about 6 degrees centigrade, it may be catastrophic. The probability is not large, but it's not zero, and it's not tiny either. And so you have to think about that.
Welcome to Today I Learned Climate, the show where you learn about climate change from real scientists. My name is Laur Hesse Fisher, and today we're talking about risk and uncertainty. If you're anything like me, then you want an easy answer about climate change. How will it affect my family, my business, my country? When is this all going to happen, and how much do I really need to change? When we interviewed MIT professor Kerry Emanuel about hurricanes, we also spoke about where the uncertainty is in climate change. And he told us about how he speaks with business leaders and politicians about risk. To really get into this, there's two things that you should know. The first is the Earth's climate is complicated.
We're dealing with a very complex system. We have many, many interacting components. We have the transmission of radiation through the atmosphere, the wind coupling with the ocean circulation of the land surface, the whole biosphere, which interacts with all of that. I would say it rivals, say, the human body in complexity. We have all these different subsystems, like we have hearts and livers and intestines. And if those parts start to function differently or, God forbid, fail, it's going to affect the whole organism in ways that even today, in some ways, medical science doesn't perfectly understand. Just as the Earth's climate has these subsystems, and how they interact with each other is complex.
The second thing you should know is that it's hard to map that complexity.
When we talk about a climate model, it's really an algorithm, which is a way of solving a very complex set of equations that govern the behavior of a system. And those equations were not just pulled out of thin air. They're actually the equations that we know govern the behavior of physics.
If we wanted to create a perfect model for how every part of the human body works, you'd have to know what's happening on the nano level, like the subatomic level, for everywhere in your body. Well, it's kind of the same for our climate system.
To make a perfect model of the system, you would have to be able to calculate things as small as a cubic centimeter or so, or maybe less, to do that. And we have nowhere near the computational firepower to do that.
A good example of this is clouds. As we know from our previous episode with Professor Dan Sitso, the particles that help clouds form behave very differently depending on where you are in the world. But as powerful as computer climate models are, even clouds are, for the moment, just too small for the models to take into consideration.
Clouds are very, very important, but the clouds may be 10 kilometers across. You can't resolve that with today's climate models. They're too small. And yet, if the climate model didn't have some representation of them, it wouldn't work. And so we have to tell the climate model that they're there.
So you had written that there are roughly 40 climate models used by different organizations around the world, and they all give somewhat different predictions on climate change. So why do they differ from each other?
They all make different assumptions about what's happening on scales that are too small for them to actually compute. And it is a way of dealing with, it's not by any means a perfect way, but it is a way of dealing with uncertainty. So you have different groups making different assumptions about how to do this, running different models and comparing them.
What's neat is that this is an essential part of science. If we don't know something for sure, then we want scientists to take different assumptions about what could be and run them through their models so we can see what the most common outcome would be. It's like getting quotes from different contractors or advice from multiple consultants. You hear what each of them say, and then you compare them, and then you use that to build a picture of what to do. This is like what the scientific community does, and they are really transparent about it.
One of the most fascinating and interesting and useful parts of science is actually quantifying our own ignorance, quantifying the level to which we're uncertain. Let me take a everyday example. If I were to tell you as an atmospheric scientist that the temperature tomorrow A high temperature in Boston would be 50 degrees, but it might be as warm as 53 or as cold as 47. Most people understand that, you can't make a perfect weather forecast, that there's uncertainty in it. And that doesn't mean that we are completely ignorant about the weather, right? It will be somewhere in that range.
As a side note, Professor Emanuel isn't saying that climate change is like weather. Weather is like your mood, where climate is like your personality. You might generally have a sunny disposition, but you're gonna feel grouchy sometimes. In the same way, weather may change day to day, but it's guided by something much larger and more constant, the climate. Okay, back to Professor Emanuel.
Good scientists are careful to quantify the uncertainty whenever they say anything about the future, whether it's a weather forecast or a climate projection. It's absolutely essential to the final step that everybody really needs and wants, which is an assessment of the risks associated with climate.
Risk. If we aren't sure if something really bad is going to happen, we think of it in terms of a risk, like our house flooding or us getting an expensive medical bill. It's why we buy insurance. Because climate change also comes with a level of uncertainty, it's helpful looking at it in terms of risk. So this next part is a little bit less about the science of climate change and more about how decision makers and really all of us can think about risk. What Professor Emanuel says here has stuck with me more than anything else in this podcast series so far.
When we make decisions about risk, we rarely make decisions based on the most probable outcome. Let me take a really simple example. You're walking your daughter to school, you come to a busy intersection, across which is the school bus, which has just pulled in, and you're a little bit late. Now you can let your little girl run for the bus, and let's say in your own mind there's a 2% probability she'll be run over on the way.
Okay, I know that's a little dark, but let's continue with the example.
If she doesn't run, you'll have to take her to school because she's going to miss the bus. Now, the most probable outcome is that she'd be fine, and yet that's the last thing you do. And all that illustrates is that to get the risk, you have to take into account two things: the probability of the outcome and how expensive, not necessarily in monetary terms, the various outcomes are.
So how likely it's going to happen and how bad it would be if it did happen.
Yeah, that's right. Both. You have to take into account both. Well, that's a metaphor for the climate system. The most probable outcome, the way we see it, is if we double carbon dioxide, we'll have a temperature increase of about 3 degrees C.
An increase like this comes with some really dramatic impacts.
You have to start moving structures that are right on the coast inland or putting them up on pilings. You have to change your agricultural practices. You have to deal with huge immigration pressures because there are parts of the world which are already agriculturally marginal who will cease to be able to do any agriculture at all. So those people are going to want to move. So you have to deal with that. We're already dealing with it. And it's disruptive, but it's not so far a catastrophe.
The thing is, a catastrophe is inside the realm of possibility.
If it's 5 degrees centigrade or 6 degrees centigrade, it may be catastrophic. Catastrophic is going to kill you, or it's going to really harm civilization. The probability of it being 6 degrees centigrade is not large, but it's not zero, and it's not tiny either. It's somewhere down there. Maybe it's low probability, but it's also low probability that your daughter will be run over if she runs for the school bus. You still have to think about it.
Scientists have created a range of scenarios of what may happen with climate change. Some people who look at the data think that our society should prepare for what scientists say is most likely to happen. And some people think that we should look at either the best or worst that could happen, even if it's unlikely. When reading about climate change or listening to advocates or policymakers, you can try to understand which scenario they're planning for, because what we do and how quickly we act will differ a lot depending on which future we're planning for. So, what about you? What world do you think our society should prepare for? The unlikely one where climate change doesn't really impact us much at all? The likely disruptive future? Or the unlikely catastrophe? You can tweet us at TIL Climate. And if you're interested in learning more about these different scenarios, then check out our show notes on tilclimate.mit.edu. Thanks for joining us today on TIL Climate, and thanks to Professor Emanuel for speaking with us. I'm your host, Laur Hesse Fisher from the MIT Environmental Solutions Initiative, and I'll see you next time.